Okay, the next little concept we need to talk about is efficiency. And at the end of the last video, we talked about how if you have an object at some height above the surface of a desk or the floor, it has some gravitational potential energy. And when you drop it or let it go, it loses gravitational potential energy because it's losing height, but it gains speed as it falls. And so it's gaining kinetic energy. And if when it hits the floor, in theory, all of its gravitational potential energy should be turned into kinetic energy. Now, I say in theory because if there's a lot of wind resistance or something, then some of it might be lost to friction. Over here, the same thing. There's elastic potential energy stored in this spring when I stretch it out. And when I let it go and it begins to move, it loses elastic potential energy, and that elastic potential energy turns into kinetic. And so if there, again, nothing lost to friction, there should be a point where x equals 0, where all the elastic potential energy will have become kinetic. So when we look at efficiency, efficiency is about how effectively or efficiently a system changes one type of energy into another, okay? Or how efficient or how well something uses the work that's put into it or the energy that's put into it and converts it into useful work. So for example, like think about your microwave. Electrical energy is fed into your microwave. You plug it into the socket. And the microwave takes that electric energy and turns it into thermal energy to cook your food. So what percentage of the energy you're feeding in through the wall socket is used to cook your food, that would be how efficient the microwave is. Or there's electrical energy running your lights, and the lights are turning that electrical energy into light energy, right? And so how efficiently does that happen would tell us like how well it's taking or how much of the electrical energy going into the light is being given off as the type of energy that is actually wanted, which is illumination. We know that light bulbs are not really all that efficient because if you touch them, they're hot. So that means they're losing a lot of that electrical energy being fed in. They're losing it as heat. Okay? So then efficiency refers to how well the work or energy put into an object is converted into useful work or energy. So how well work or energy put into an object is converted to, maybe converted into is more proper English, converted into useful work or energy. So back to the example of the light, the useful work or energy would be the brightness of the light. The unuseful would be the heat of the light bulb. Okay? So we have an equation. It can be written actually in two ways. So efficiency is equal to, one way is energy out over energy in times 100. And the second way is really the same thing if you realize what work is, because it's equal to work out over work in times 100. When I say they're the same thing, remember work done is the change in energy. So the shorthand way would be EFF is equal to EO over EI times 100. Or EFF is equal to WO over WI times 100. Does it matter which one of these you use? Nope. I will usually use work if in the question it says the work done on, and I'll use energy if in the question it says the energy, but in the end they're exactly the same thing. It's going to give you a percentage, right? No units because the units are going to cancel the top and the bottom, and it's going to give you a percentage. This percentage will, well, at best it could be 100%, but not in the real world. nothing is 100% efficient. When we're talking about microwaves, they're usually the newer ones now. They're usually around 80, 85, which is really good. When they first came out, they were closer to 60. Our light bulbs are probably about, I don't know, maybe 15% efficient. A car engine, how efficiently it turns the gas into the drive of the car. If you're lucky, it's maybe 70% efficient. If you look at, if you've gotten a new like washer, dryer, or stove recently, or maybe any major electrical appliance, it will have a sticker on it that will tell you the efficiency. How well is it using the electrical energy you're feeding into it? But remember, nothing can ever be 100% efficient, and certainly not more than 100. One of the harder parts for people when using this equation is figuring out which one's the in and which one's the out. Well, if this can never be bigger than 100, then the number on the bottom always has to be bigger, okay, than the number on the top. So you got them in the wrong spot if it isn't. Usually we're pretty happy if anything's like 75% efficient or above. A laser is about 1% efficient, okay? And so your last set of homework for tonight will be with this this equation, okay? So you'll have Hooke's law, you'll have elastic potential energy, and these guys, all right?